So yeah, thanks for having me. I'm excited to give a talk about DuckDB and Lambda functions in the Duck's nest. Mostly a wordplay I came up with. We will dive into that a bit later. So yeah, who am I? I'm Tania, and I study computer science in Ilmenau in Germany. And now I'm a software engineer at DuckDB Labs. I also did an internship at the CWI at some point, which is the birthplace of DuckDB, and it's how I got to know people in the database architectures research group there. So then eventually, sometime after my internship, when DuckDB had become a startup, people reached out, and yeah, now I joined the team. And what DuckDB Labs does is, yeah, it provides development and support for the product DuckDB. So yeah, what is this DuckDB? I'm also not sure how familiar the audience is, so I decided to have a small introduction first and then dive into the specific topic of my talk. So DuckDB in a nutshell, it's an analytical database. So analytical workloads. It provides extensive SQL, that means the basic SQL syntax, but also stuff that we added or that's in the community that makes it, for example, more friendly to use. It's in process, so there's no client server setup. You can run it on your own machine as like inside the process using the database. It's written in C++11, so it's fast, and the development started in 2018, so it's also a fairly new system. And here on the right, I have some points that I will mostly focus on in this presentation and that are going to be brought up in the next slides. So free, this is, yeah, the idea of free here is not, okay, so sorry, I'm a bit nervous. So DuckDB is on GitHub, so it's there under the MIT license, so anybody can use it. And as you can see below, in the recent months, the usage and people starring it on GitHub has like gone up a big lot. So that's of course makes us as developers very happy to see its adoption. And another point I want to mention here, it's not only free to use, but because it's an in-process system, what's also the case is that you don't have to buy expensive cloud software to run it or to set up a server somewhere. Then, but you can run it on your laptop. So you also maybe don't have to pay cloud costs. And then it's fast. So recently, ClickHouse, also an analytical system, published their benchmark called ClickBench, a very good benchmark. And when we went to our recent version of DuckDB, we actually managed to beat them in the benchmark. So that, of course, was really cool. And yeah, I want to showcase it here to show that, yeah, it's a fast, modern database. So that was the small introduction to DuckDB and some general information on that. But I now want to go to the main part of my talk, which is to talk about nested data in DuckDB, which is something that I've worked on over the last years now. And yeah, so let's first have a bit of a discussion on the relevance of nested data and later also on lambdas. So why is that relevant for DuckDB? Well, I already said that we do analytics. And in analytics, nested inputs are common. For example, JSON. A lot of people, they query data that they have in JSON formats, and extracting the data into a relational database system, which DuckDB is, can be cumbersome. And also, aggregations are not necessarily intuitive on nested structures. And often you would, for example, have to perform some unnesting steps before you can actually start your computations. And because this happened very recently, I decided to include it in this presentation. There was a person, I think on Twitter or LinkedIn, and he wanted to query a data set, and the data set was stored somewhere else in Parquet files. And he had to query a lot of these Parquet files, so he generated himself these very complex queries. You can see here, he tried to use union all, to union all the selects of the different files. And later he tried to use read Parquet and had a list input, so only the strings of the URLs of these files. But eventually, because the tweet got quite popular, someone poked him to use DuckDB's list transform. which turned this into a much more elegant solution, because now we can actually have like a pattern URL, and then we just generate the remaining ones into a list from that. And yeah, I was excited to see this because it was a really cool use case of DuckDB's Lambda functions, which are a specific function that we provide or that we support on these list types directly without unnesting or anything. So yeah, just a bit more on that. This type of support for lists and nested types is not necessarily typical for a relational database system. So if you look into the landscape, you can see that a lot of schemas like data types don't include nested types like lists, structs, or maybe maps. So if users want to use these systems, they are prior to importing their data, for example, forced to normalize the data. What you could also do is there are more specialized systems that support nesting, but then they are maybe not necessarily your pure or your very common SQL engine systems. And what you can also do is you can pay money, and then it's likely that you find a system that does both. And now what I also want to mention here, now you could say like, oh, but Postgres is free and it has nested data support. It does, but Postgres is an analytical system, so it might not fit the use case. So now that I talked a bit about nested data, nested types, and why that is important and interesting for our analytical use case, I want to highlight this list comprehension that I already hinted at earlier. Yeah, so if we think of list comprehension, I just started here with a Python script because, yeah, it's our favorite scripting language, and a lot of easy to use ideas like easy programming use ideas come from there. So here we have a list, just a list of women in computing, and we want to get all the women that have an A in their name in uppercase. So for X upper, for X in the woman list, if A is in the name. And now we just print that list. Now what we did, or what we implemented and added to DuckDB, is to support the same in SQL. So here we can create our table. We have a people table. One column is the woman column. It's a list. So this is like a list data type. And we insert one row into that table, which contains the above list. And now we can use the same list comprehension syntax to query this data and perform the same computation. And we can see we have to alter it a little bit because, for example, uppercase, we use the SQL upper, which is like this. But it's mostly the same, and we get the same output. So before I dive into how DuckDB does it, I first want to look at Python and why we can, for example, why you might not want to use Python if you have a big table with a lot of nested data. So Python, if you look at this example, I changed it a bit. So we use numbers because it's a bit easier to follow, I hope. We have an input list and we want to add 1 to each element, but only if that element is greater than 1. And then the result will be 3 and 4. So we can write a sequential program here. We get our input, we have our result, which is empty, and then we loop over each list element. And then for each element, we check if it's bigger and we append it to the result. But this doesn't scale. There's a lot of open questions here that make this not feasible if we want to do analytical data science on bigger data sets. Like if we have plus 1 million rows, we cannot run a loop inside a loop and do these computations. It also doesn't support more complex Lambda functions, or at least it's much more complex because you have to write your own function for it. And or at least it will not use a nice engine on these functions. And then there's also like the thing that we had a lot of research on how to do fast computing on a lot of data. For example, vectorization, tight loops, cache proximity, but we cannot really use that as is here. So that's why implementing this in a dedicated analytical computing like database system was something that we wanted to do. And because then we can use all this stuff, the research that is already there and that we have in these systems to make this fast. So yeah, let's look into how DuckDB does it. And there's two phases to it. One is like getting to the execution from the syntax, and the other part is the actual execution. And I will start with that because I hope that's a bit more, gives a nicer basis for the second part. So if you look at DuckDB, our lists or our input is going to look like this. We have two columns in our table. One column is the list column, which contains these nested types. And just for the sake of an example, I added also an integer column here. And now if you look at the internal layout of that list column, we first have, DuckDB uses vectors internally to store data. So we get a vector, which is only the offset and the length of the list for each row. So this vector has two rows, and then the first row is 0 and 3, and the second 3, and the length of the list is 2. And now the actual data we store in we call it child vector, which only holds the list elements in a sequential order, or actually any order, because what we can do is we can use a selection vector that says where we find the matching elements. So at index 0, we find the 7, at index 1, we find the 12, and so on. So this is the internal data layout. And yeah, with this, we can make use of a lot of concepts that are really nice because they make things fast. We can process this vector at a time. Ideally, our vectors are small enough to fit in the CPU caches, and we can use even tight loops to run computations on them. And now, to start with a slightly more complex example than the previous one, we want to add this column n to each element of the list x for each x in the list. And this is for each row, but only if that element x is smaller than 10. So just a small setup. This is again our input, and this will be our result. So 12 is not considered because it's greater than 10. Same for 11. And for the first row, we add 2 to each element, and for the second row, we add 3 to each element. So if we walk through this a bit more to see the specific steps, we can again look at our input here. And the first step would be filtering out all the elements for which we don't have to perform any computation, any transformation. So we filter out all the elements that are smaller than 10. Something that I want to highlight here is that ideally we don't want to touch the actual data. So because we don't know what's in that, right? That can be further nested, it can be expensive strings. We don't want to, ideally we don't want to touch that. So what we can do is we can just adjust our selection vector. We don't even have to end the base vector. And we don't have to look into the child vector and change anything there. But we have to look into it, but no changes, sorry. So we can see that for the first list, the length will be now 2 because we filtered out one element. And for the second list, the length will be 1 because again, we filtered out one element. And also their offsets in the selection vector changed. So the selection vector will now be pointing to first element is on index 0, second element is on index 2. For the second list, index 3. And now that we have that, we need to add our second input vector, which is 2 and 3. But the problem here is that this is on a row basis. So first row is 2, second row is 3. But we need to map this to, as we can see, 3 elements. So we expand this mapping to the individual lists. So for the first list, which is 2 elements, we put 2 zeros in the selection vector. And for the second list, which is only 1 element, we put a 1 to point to the 3. And now what we can use is we can take these 2 vectors and compute them like parallelize over the elements for the computations. And all of that happens in the back. DuckDB does that for us. It can run complex expressions on vectors as long as you have already provided them in the format that it expects. So yeah, it's a bit weird for me to not get feedback in these online presentations, but I hope everybody's still somewhat on board. And yeah, now we have the result, and we can see we didn't touch the 12, we didn't touch the 11 because it's not relevant. But we now had to change the data. We changed the 9, we added 2 to the 7, and we now have the 7 because we added 2 to the 5. And the same then for the second list, which is now 4. Yeah, so this is how we do it in the execution. And the key point about the execution is to prepare the inputs so we can just throw them into our expression execution engine. That engine expects vectors. It has this expression it needs to execute. And once we have all our vectors, like for example, expanded and prepared, it will just fire off. So yeah, that's what we did here. And now the harder part about getting this to run in DuckDB was everything before that. Because we need to pass this list comprehension syntax into something we understand. We need to use the transformer to create these constructs that we can understand, and then we need to bind them. And let's have a look. So again, the same query here. So we could first pass the syntax, that's fine. And we pass it into our pass tree. And now what the transformer is going to do, it's going to take the syntax and we're going to turn it into scalar functions, because we understand scalar functions in DuckDB. So afterwards, it would look like this, which we also support as syntax, but the list comprehension is just neater, as you can hopefully already tell a little bit. So after we transform this, it will look like a list transform, which takes, again, a nested list filter, which takes the input list, does the filtering, and then does adding the extra column. Yeah. So just looking at the syntax here a bit more of one of these two scalar functions, I chose list filter. We can see the first parameter is the list input, and the second parameter is this whole construct, which consists of a lambda parameter and on the right-hand side, a lambda expression. A few remarks here. The lambda expression can be very complex, like basically anything that you could have in a SQL expression. And the lambda parameter, well, the list filter expects 1, but for example, which is actually on the roadmap, a list reduce would expect 2 parameters here. Yeah, so this is the parsing transforming. So now we have our scalar function, which we already know, and we can continue from there. So looking a bit more into this, when we try to bind this scalar function, we have one thing which is these lambda parameters that I already mentioned. Here it's an x, for example. For this x, we have to get the logical type. So we can look at our list and we can see what our child types are. And then, so we can, in order for us to bind it, because the binder wouldn't know, what is this x? I don't know what to do with that. We create a dummy table, we call it our lambda table or whatever, and it will have this one column called x with the data type. So yeah, we fire that off when we bind this expression, the right-hand side of the arrow. So because we created this dummy table, we can now actually pretend this is just any SQL expression we would get, and the binder is happy, and it will say this x is a column reference to our dummy table. So that's cool. We bound the lambda function. The problem is, once we reach the execution, we're going to find out, oh, that table doesn't actually exist. So what we have to do is we need to add some extra steps so that later on we understand what data we can expect. So what we want to do here first is index calculation, because what we did now is we just gave this lambda parameter the index that we would expect, because it is this dummy column in the table. So how does index calculation work here? The execution expects a lot of vectors that it can execute on. And this list of vectors, they all have their indexes. So now what we have to tell DuckDB is that if we see an x in our expression, we're going to find that in the first vector, which is going to be index 0. And if we find an n, it's going to be in the second vector, which is going to be index 1. And if we adjust that correctly in the binding phase, we can just fire off our execution. This looks simple enough for this type of expression, but it can get more complex because expressions can get more complex. We can have recursion, like you can have a scalar function inside a scalar function inside another one, however deep you want to nest it. And you can also have a lambda function inside another lambda function, which we saw earlier because we had the list transform and the list filter. So for example, just looking at a more complex example here, we want to calculate the logarithmic result of adding, of this computation. And actually what's interesting here is that we have x and y, and let's pretend they are both lambda expressions, but one of them is going to be the current or the inner lambda, we can say, and the outer one is like one nesting layer outside. So the current one will be index 0, then we have index 1, and then we get other indexes for all these other base cases here. It's not necessary to, like the thing that I want to highlight here is that this can get very messy because we have to recurse into our expression. We have to remember how many lambda functions did we already see, and then we have to adjust all these indexes that we actually already got from our binder. So yeah. And then once we've done that, there's one last problem, and then I'm done with all this lambda stuff. So which is captures. Because the way our scalar function arrives is with two parameters, this list and this right-hand side, left-hand side expression thingy. And this is, we cannot understand in our execution. So what we have to do is we have to take this whole second parameter out of the function and add it to some global execution state so we can use it later. And then what we have to do is, after we found all these recursion base cases, we also have to add all of them as parameters to our list filter function, so that later we will get all these vectors that we need, that we had now actually set all these indexes for. Because otherwise, if we don't do that, the execution engine doesn't know which vectors to pull. So if we don't adjust the input parameters here and say, we need this parameter, this parameter, this parameter, later on, we will not know what we need. So yeah, just to sum this up a little bit, what I wanted to highlight here is that you can get these things to work in a relational database engine, in an analytical system, but it takes a lot of tailoring. And in the end, the results will be very satisfactory because what we gained here in the end is that we, even though maybe the binding and everything gets much more complex, we enabled all this heavy work that our execution engine already does to run on lambdas. And yeah, so as I already said, it was quite a journey, a lot of edge cases, a lot of brain knots, but yeah, eventually we got there and we got it to work, and then it was slow. So just very recently, that's also why I decided to talk about this specific Lambda stuff. We did this, if you see here, the top PR is like Lambda performance revamp, basically trying to make it fast, which which actually worked, and it's now in our cutting edge version. So yeah, either give that, if you want to give it a try, pull the recent master or wait until our next release, and you can, you can already use this cool list comprehension syntax, but if you want to have it even faster, you can use DuckDB's most recent release. Yeah, so give DuckDB a spin. You can just get us pip install or check out our documentation if you want to run in a different language or platform, whatever fits your use case. And yeah, that was my presentation. And yeah, I'm curious if there are any questions. Thank you.